Thank you, Alex, and many thanks to Andrew for kicking off Transform. Please join me in welcoming our next speaker, Raquel Urtasun. Raquel was the Chief Scientist and Head of Uber ATG Toronto. She's a professor at the University of Toronto and a Canada Research Chair in Machine Learning and Computer Vision, as well as co-founder of the Vector Institute for AI. Raquel is truly a world leader in the field of computer vision. She's been recognized with the NVIDIA Pioneers in AI Award, a Ministry of Education and Innovation Early Researcher Award from the Canadian government, among other awards for her research. We're very excited to have Raquel at Scale Transform this year. Welcome. The stage is yours.
Hi, my name is Raquel Urtasun, and I am a professor at the University of Toronto. Today I'm going to be talking about the future with affordable self-driving cars. We've seen a lot of investment, more than $20 billion, that has happened since the DARPA challenge 17 years ago. And unfortunately, despite this investment, we are so far from having a commercial solution to self-driving. And the industry is really at an impasse. So we need something different. We need self-driving 2.0. In particular, there is two main things that actually really help in the progress. On one side, we need to be able to develop autonomous systems that can solve the long tails. And on the other side, we need real-time high-fidelity closed-loop simulators that have the right level of fidelity such that we can test and train our autonomous systems. In this talk, I'm going to show you the next generation of algorithms that really follow and solve these two problems. But before I do so, I'm going to start by talking a little bit about what are the current approaches to autonomy, such that I can contrast our technology. In particular, if you look at almost every single player out there, the way that autonomy works is that the vehicle senses the environment. In this case, I'm showing you the LiDAR seen from the top. And what everybody does, or almost everybody, is to localize the vehicle with precision of a few centimeters, such that you can use high-definition maps, which provide a lot of information about the static part of the environment without you even look at the sensors and see it there. Then the vehicle has to perceive the area around you with all the actors of interest and predict potentially what they're going to be doing in the next few seconds, such that we can plan a safe maneuver that will bring us to our goal, making progress in a way that is safe. And this process is typically repeated around every 100 milliseconds or so. Now, this traditional engineering approach, which is very reminiscent with the approaches that we've seen 17 years ago in the DARPA challenge, is based in a very robotic-centric approach with a lot of hand engineering models. The good thing is that it's interpretable. It creates these intermediate representations that are very important for validation and safety. It's also easy to incorporate prior knowledge, for example, the rules of traffic. However, there is a few key problems that really prevent this technology from scaling to solve real-world problems. The stack is typically developed in silos, so models are not trained for the end task, and they are not developed with a holistic approach that really will come up with more optimal solutions. There is very small interfaces between these models, resulting in cascading errors. You can think about it as you go into more and more complex reasoning, your system gets more and more blind. Furthermore, every time that you observe a problem on the road, instead of trying to have a principled way to solve this problem, what teams typically do is that they develop models that solve very specific subproblems. For example, whether there are leaves on the ground or whether you can see exhaust in the later point clouds. And even more, there is very, very bad developer productivity because every time that you change something on the software stack, you need to adjust everything else, which is super tuned as a manual process, going one model at a time, and there is hundreds of these models. As a consequence, a change that is small takes even a quarter or more to actually land in production. And since this software stack are very complicated, you need hundreds of people to actually be working in developing this technology. So this is not a solution that scales. There has been a few people that have been looking at, can we use an AI-first approach that try to solve self-driving? The advantage is that this will be very, very simple, right? Instead of many, many models, you will have a single system. And it can be trained for the end task of driving. So every time that you actually make progress, basically your system will drive better. However, such a system, you cannot really incorporate prior knowledge. Is also very difficult or impossible to get interpretability or to be able to validate the system, which is a problem, right, for regulators if you want to have this, at the scale in our roads. And it's not super modular. As a consequence, you need way too many examples in order to to be able to solve complex tasks. And these examples, right, in order to handle, for example, a situation that is, say, with an accident is imminent, you actually need to observe such a situation, which is unethical. So this is also not a solution. In the past few years, we've been developing a new generation of algorithms, which basically has the advantage of both the traditional approaches as well as an AI-first approach, which are really, you can consider as self-driving 2.0. We can handle the long tails through a new generation of AI technology, which combines deep learning with probabilistic inference as well as complex optimization. And this allows us to do complex reasoning and learn from a few examples and generalize much better than any other technology out there. We produce interpretable intermediate representations, which are fundamental for validation and safety. Our system is end-to-end trainable, so we can have much more complex functions than in traditional stacks, even accessing raw sensor data across the full stack. Since all models are trained for the end task, they basically, every time that you make any changes that are positive changes, you will end up driving better. And we don't have cascading effects of errors because every one of these models can be as complicated as you want and can access raw sensor data and therefore you can basically correct for mistakes. Furthermore, since you share computation, you have much lower reaction time than traditional approaches. So let me show you a bit of the evolution of some of these methods as we developed in the past couple of years. We started by looking at, can we actually have a single system that is able to solve perception and prediction? So the task of perceiving everybody around you and predicting how the different actors are going to be moving in the next few seconds. And it turns out that neural networks are very, very amenable to this, and they can do it much better than traditional systems. And the first version that we built was very simple, where we input LiDAR point clouds as voxelized representation, and we have a simple neural net that does both detection as well as regress to the targets of where we expect every single vehicle to be in the next few seconds. So I'm showing you here a video where the system can do detection, tracking, as well as prediction into the future with a single neural net, all under 30 milliseconds. And you see that it's very, very accurate and can handle very complex situations. So here the same color means that we are tracking a particular object across time. And this dots emanating for every vehicle is basically the predictions of where they're going to be going in the next few seconds. So you can see that we can do very accurate predictions with just this simplistic model. We can go one level deeper and try to predict more sophisticated things. For example, semantics about the intention of the different actors that are very important in order to produce better motion plans. And on top of this, we can also have more sophisticated inputs to our neural nets by exploiting as input also the high definition maps in case that they are available. I want you to focus in this video on the bottom, where the different colors represent different intentions that the network is thinking for the different actors. So the more yellow it is, the higher the probability of just driving. The more red it is, the higher the probability of arriving to a stop. And the more purple it is, the higher the probability of being parked. Furthermore, the arrows represent also another set of actions, whether we're going to take a left turn, right turn, or whether we are in the process of changing lanes. And this extra information, right, these semantics are actually super useful for motion planning. Now, if you look at these systems, right, so they're much better in terms of performance than traditional approaches to perception and prediction, but they have one fundamental problem, which is that they predict every actor in isolation, independently. And as a consequence, you might end up with a solution like the one that I'm showing you here in the video, where both things it's likely for each one of these trajectories to be possible. But as a whole, this is not a scenario that is likely to happen, which is a collision. Instead, if you think about what happens in an intersection like this, one should take into account the interaction between the actors in order to reason about maybe actor A is yielding to actor B, or maybe it's actor B that yields to actor A. So the next thing that I'm going to show you is how we can incorporate this kind of reasoning in neural networks. So in order to look at the interactions between actors, we're going to use a more sophisticated neural net. In particular, we're going to use a graph neural network, where basically it's going to take some input representation for every one of our detections, and it's going to pass information between all these different actors in the form of message passing. And after that information is passed, the network is going to decode into what is the most reasonable trajectory, as well as some notion of uncertainty for every one of these actors. Okay, so it's going to predict a marginal probability, but taking into account how the different actors interact. So here in the video, I'm showing you the system in action, where you can see sophisticated scenarios. And you see how it's predicting much better predictions in terms of uncertainty, as well as in terms of what are the potential interactions between these different actors. But one of the problems with this is the fact that actually it's still predicting a marginal distribution across different trajectories and different actors. So what does this mean? Imagine we have the following situation where we have two cars driving next to each other in two different roads, and these roads are going to merge. If I'm predicting the marginal distribution of every one of these actors, and I'm going to use it for motion planning, what happens is that I'm going to sample from this marginal distribution independently for every actor. So this is a potential sample that can happen where the first actor is going to basically accelerate, and the second actor is gonna yield, and this is a pretty reasonable explanation. Maybe the opposite can happen when I sample from this marginal distribution, and this is also a reasonable explanation. Maybe what happens is that the two independent samples can tell me that maybe both cars are actually yielding to each other. This is not super reasonable, but can happen in practice, so that's okay. However, I can come up with, as I sample from this marginal distributions, I can come up with explanations that are actually not reasonable. For example, despite the fact that I build this marginal using interactions, what happens when I sample from it is that I can have explanations where basically I would end up with the two vehicles occupying the same space and therefore having a collision. So we need to have a much more sophisticated way to really reason about the whole scene as a whole. And the question that arises is, how can we do this in a way that is computationally efficient? Because we need to do this on the vehicle in a fraction of a second every 100 milliseconds, right? We need to have this complex reason. And this is the reason that has prevented people from really building representations that can really explain the scene as a whole. And when I say explaining the scene as a whole, it means that when I sample from this distribution, I should have full explanations of the scene. So this is one sample where basically all these actors are waiting, and this guy is basically taking a turn on the intersection. So this is a very a good explanation of the scene. And if I sample again, I would have a very different explanation where basically these guys are all going, and therefore this guy is waiting. Right? So now I'm really taking into account very consistently what are all the possibilities across all the actors instead of doing this one actor at a time. And the question is, what is the technology that can allow us to do such a thing in a fraction of a second? So it turns out that we can use deep structure models in order to do this in a very, very reliable way, and also such that inference is actually really fast. So in particular, we build implicit leading variable models where basically we have a representation of the scene which is distributed, and this representation captures all the stochasticity about condition on the inputs about the scene itself. And we have an encoder and a decoder based on graph neural networks such that, again, we take into account all these different interactions. And this type of system can, works much, much better than anything that you see out there. So multipath, for example, here is a Waymo's prediction system. And the lower, the better it is. And you see that, these systems can do much better in terms of all the metrics compared to anything out there. Again, by doing this complex reasoning, where it's taking into account how everybody, potentially could behave in an intersection, right, or could behave in a particular scenario, but in a way that is holistic. Just showing some qualitative results so that you can get an understanding of how complex situations can be handled this way, like super notches as you just saw. And again, these predictions are super, super reliable here and very multimodal. And when you hook up such a system to a motion planner, you end up with much safer plans, much more comfortable driving, and equal progress towards the goal. Now, as we look at the development of these, autonomous systems or perception and prediction systems, they are as good as your sensors, right? So if you use LiDAR, if you use cameras, right, there is as much, you can solve scenarios for the things that you can actually observe. And this is a very big limiting factor of current technology. So imagine you have the following scenario, which is, again, seen from the top. This is the LiDAR point cloud. So for some of the, say, actors around the scene, you're going to have a lot of observations, right? So it's actually very easy to detect and predict what these actors are going to do. For some of them that are far away, you're going to have very little evidence. So it's actually very difficult to make any precise detections or predictions. But it's not just about being close versus far away. There is also a lot of occlusions that happen, because of parts of the scene, because of other actors, and there is many areas where you're basically blind into what's happening. And this could be a kid that is actually running out of occlusion and is going to jump in front of the driving car, right? So this is actually potentially very problematic for safety. But this is as much as your eyes in the driving car can see. So one thing that we could do is, if there will be multiple cars in this scene, we could potentially enable communication between these vehicles such that we could have much more accurate estimations about what's happening in the scene, because we could see through occlusions and see further away as if things would be closer. So the next question I'm going to try to answer is, how can we use AI to build vehicle-to-vehicle communication systems in a way that we can get again, real-time performance and really take advantage of the fact that many vehicles will be on the same scene. So just another way to think about this is that imagine there is a scene and vehicles with different colors are basically self-driving vehicles. There's going to be also some other vehicles driven by humans, right? And every vehicle observes the scene and they see the scene in very different ways, right? From different viewpoints, etc. Right? So the idea is, can we actually have a way such that these vehicles can communicate and we can exploit this information in a way that we can do it very, very efficiently and basically improve a lot of performance. So if you want to do this, there's like two questions you need to answer, which is, how can I send information that is going to provide me with the best trade-off between how much bandwidth do I need in my network, as well as how much information is sent such that my perception and prediction systems get as better as possible, as best as possible. So there is different sorts of information that you can send. On one extreme, you can send the raw sensor data. However, you will need a lot of bandwidth for this, right? And also you will really overwhelm the receiving system, because not only has to process its own sensor information, which is already difficult to do in real time, now you're going to have all the sensor data from all the other vehicles. So this is not a good solution. Maybe what we can send is the output of the perception system or the prediction system, and then somehow combine it afterwards. This has the advantage that we need to send very little information. However, if we make mistakes, we're just going to send garbage. So, and we have basically, almost forgotten everything of what we have observed. So this is also not great. So our approach is very different, which is to say that we can actually learn some intermediate representations of our processes such that we can compress them and only require very little bandwidth, and at the same time retain all the key information in order to make the best out of this multi-agent system that can do perception and prediction. And you can think of this as the fleet is a distributed system for computation. So the way it works is that every vehicle is in the environment, it senses the environment, it's going to do some level of processing, it's going to compress the information, send to the medium, and then basically we're going to use in every vehicle, especially a word graphing network that combines all the information to perform better perception and prediction. Okay? And it turns out that compared to node fusion here is if you actually have a single vehicle in the scene, you can get extremely significant improvements in terms of both perception as well as prediction over here. And what this curve is showing is that this system scales super well, and the more vehicles that you have in the scene, the better you can see and the better you can actually perceive the world. And this is in terms of perception, and here error decreases in terms of prediction. Okay, so this is a very, very significant improvements in performance. Now, I've shown you how to do different levels of complexity in reasoning across perception and prediction, as well as how to exploit vehicle-to-vehicle communication such that we can see beyond, beyond occlusions, etc. Next, I'm going to talk a little bit about how we can actually go one step forward to build full autonomous systems that have all these nice properties that I was mentioning at the beginning, where through deep structure models, we can handle the long tails, we can create interpretable representations that are fundamental for safety, and the system is end-to-end right now. So, and I'm going to start with a more simple version, and then I'm going to show you a more sophisticated version. So the first version that we created was something where, again, the input is going to be the data point plots and the map, and we're going to output not only detection and prediction, but also a cost volume, which we're going to use for planning. And this cost volume represents what is the cost for the self-driving car to be in any particular location in space at every point in time. Okay. And we do that such that motion planning is nothing but generating a whole bunch of trajectories, indexing the cost of every one of these trajectories, and basically selecting the one with the minimal cost. Okay, so all of this process, you can do it through feed-forward networks. And you can train this also end-to-end just by having some loss for detection, as well as, in this case, we use max margin or imitation loss for the planning, since you cannot supervise the cost volume since you don't know how to do planning to start. So I'm going to show you a video that can showcase a few difficult scenarios so that you can see where we can see how we can do joint detection. Prediction, again, is going to be with this different points into the future. And I'm going to show you in color different areas where the vehicle has low cost, and the different colors are different points in time. Okay, so I'm projecting this city volume into 2D dimensions such that they can observe this. And one of the things that you see is that it can handle multimodal distributions naturally. It can also handle very complex scenarios, like somebody cutting in front of us, very, very naturally as well. And it does this simply by learning from data. In this case, it's a super notch, which is another super notch here, which has some of the most difficult maneuvers in self-driving. Now, this was a great step forward, where now we can train end-to-end the full autonomous system and get interpretability. The problem that we still have is the following, is that we are not employing a multimodal distributions, right, which is something that is important for self-driving. We are also not really explicitly conditioning planning on prediction. Instead, this was phrased as a multitask problem. And basically, we rely on the system to learn everything from scratch. We cannot really incorporate human knowledge, for example, things like that we should follow the laws of traffic, or we shouldn't collide, or we should have dynamic constraints. So in the next model, we're going to show you how to incorporate this through a more sophisticated deep structure model, where we're going to be able to use player knowledge, we're going to be representing multimodal distributions, and we're going to explicitly condition on prediction to make our motion plans. So it's going to look a lot more like a traditional stack, with the difference that we have access to the sensory data and the sophisticated features across the whole stack. And the prediction model here is going to be a very sophisticated Markov random field, such that this is where the probabilistic reasoning comes, such that we can really reason about the interactions between all these different actors. And in the case of the planning model, it's going to be a complex program to solve that displaces a complex minimization that uses a combination of handcraft costs, which are related to safety, which you need to guarantee, and fully learned costs, which are coming through sophisticated neural nets. Okay, this is a system that you can train end-to-end just from data of driving around in a few bounding boxes. Okay, so this system is able to predict much better with full multimodality. As you can see here, in some cases, it's very unimodal because it's very you're pretty certain about what's going to happen. In some cases, it's not so clear, right? So it has much more uncertainty, which is exactly what you would like the system to do. So this results in much better errors in terms of much better accuracy in terms of prediction benchmarks compared to the state of the art. It also produces, almost zero collision rate in terms of open loop and closed loop simulations for very, very difficult cases. And in general, a very big improvement in terms of planning costs. So I show you through a lens of 20 minutes into what is the future of autonomous systems. How can we use this new technology that we have developed over the past 10 years of deep structure models in order to really solve these long tails? And now I'm going to show you the first-in-class real-time high-fidelity closed-loop simulator, when we can really truly verify, test and verify the full autonomous system. So if you're thinking about, how you can test self-driving, the industry uses a combination of three things: a structured testing in the test track, which is very repeatable, but is not scalable. Real-world replay, where you're just replaying logs that you have captured, just raw sensor data, and then looking at whether your system does differently than what you observe in the world. And simulation. And simulation is extremely important because you can't really wait for observing something in the real world to be able to test whether you can actually handle versus not. Furthermore, in simulation, you can test near-like accidents or accidents themselves. And you can really simulate the long tails and therefore really test at the scale. So let's look at what the industry is doing for simulation, and I will show you this next generation of simulators, which is best in class. So recall the autonomy system, right? There is many companies that they say that they test millions of miles of simulation. What they really mean is that they start with bounding boxes and trajectories, and they only simulate test the motion plan. So it's only a submodule of the whole software stack. So this is not sufficient for testing and verifying the full autonomous system. And also they do where the noise characteristics here are actually, these are like nearly optimal trajectories. So they don't really reflect the errors of, of the perception and prediction systems. So this is not a good idea. Instead, what we need to do is we need to have the ability to simulate how the sensors will have observed the scene, such that we can test the full autonomous system. So let's see how we can do this. If you look at what is out there in the industry, what they do is that they use artists to create virtual worlds together with extremely simplistic automation in the form of procedural modeling. That is a rule-based system that basically composes scenes by just pasting some of these assets that are manually generated. And then they use either a very simplistic rendering that creates sensor simulations that are not realistic, or they try to use more sophisticated rendering techniques, but it takes, ages, hours in clusters of, 10,000 computers to even generate one frame. So none of those two approaches really scales and is in any form close to what you need to do. So our approach is very, very different, and is the following. We can use the data that we capture by just driving around the world in order to reconstruct how the world looks like automatically. In this case, I'm showing the static part of the environment, as well as dynamic objects that we can reconstruct. This is every single vehicle we have observed as we drive. And we can also reconstruct more sophisticated objects. In this case, I'm showing you pedestrians, where, from a single data strip as well as a single image, we can reconstruct how, the shape of pedestrians, as well as we can do it in a way that we can reanimate it automatically to do any sort of activity you want them to do. And I'm just showing you here some goofy postures so that you can see how well we can do the formations, etc., automatically. So with this technology, every time that you drive, you can basically reconstruct everything you have observed. So you can have simulations now at the scale. The second component that you need is very accurate behavioral simulation. If you look at the industry, what they have is, again, this very, very rules-based system, very simplistic, again, based typically on procedural modeling, which do not represent the variety of behaviors that the humans really do on the roads. And as a consequence, you can't really test how well your system will do because you're testing, against robotic agents that do not really exist. So we have created multi-agent simulation systems using AI that is able to very naturally represent, this, learn from data how, the traffic really behaves. And I'm showing you here some of the longer tail events, such as U-turns, lane changes, and I'm going to show you in a second an unprotected left, which is one of the most difficult things to be able to simulate, as you see over here. And it's very, very naturalistic. There is no multi-agent simulation system that can do things like this. And the next thing that we can have is, by combining AI with physics, we have a super, super high fidelity simulator. On the left-hand side is the simulation. On the right-hand side is the real world. And what is important to note is, in green is the output of the perception system. And as you can see, it correlates perfectly on simulation and on the real world. So as a consequence, now we really have a way to test the performance of the software stack in a way that we can really trust our results, because the behavior is the same in the real world as in the simulation. So we can create, safety critical scenarios as the one over here with our, virtual, automatically reconstructed world and traffic. And in this case, we are showcasing somebody coming out of a collision, and we are testing how the software stack is actually reacting to this by inputting just the sensor simulation. And we can see that we can actually generate this at the scale because everything is automatic here. So this is variations of this scenario across different geographies that we reconstructed, across different variations of the stack configuration of the coming out of a collision. Importantly, it's not just about simulating LiDAR. We can simulate also cameras in a way that is consistent with the LiDAR as well. And what I'm going to show you next is how we can compose existing logs by inserting automatically reconstructed objects from other logs. And I'm going to show you every scenario twice, such that you can try to guess into which ones of these objects are actually fake, weren't there in the log in the first place. Okay, so some of them are relatively easy to know. For example, this guy over here, right? The lighting is a little bit off. In some scenarios, actually, it is extremely difficult to know or to guess into which one is fake. So this one, for example, in front of us is actually fake, right? So it was, I'm sure that most of you didn't even get that, or this guy over here, right? So it's super, super realistic, this simulation system, so that we can fool humans, but also we can fool machines. So today I show you, a glance into really self-driving 2.0, how we can develop the next generation of AI algorithms with an AI-first approach, not a robotic-centric approach to try to solve self-driving. And in particular, I focus on perception, prediction, as well as motion planning, simulation, and vehicle-to-vehicle communication. Now, there is a lot more things that we do, but I hope that this showcase whether the current problems in the industry and how really this next generation of algorithms should look like. Thank you very much for your attention. This is all for me today.